Hello, my name is Brian Bulkowski. I am the CTO and founder of a small database company called Aerospike. How many of you heard of Aerospike? Hey, a bunch of you, great. So I don't have to go into too much depth there. What I'm going to talk to you about today is a little different from a lot of what you hear and think about in-memory computing. However, what some of the sizes, speeds, and feeds that you'll see here should be similar to what you commonly think of as in-memory, and there's certainly no rotational disk involved. So what happens with scalable operational databases, and what is an operational database, as opposed to the typical in-memory computing pattern that you guys have heard about and you commonly think about here at an in-memory computing conference? Well, at Aerospike, we figured out that we could build a both RAM and also flash-based clustered database that was client-server, and that's what's going to be really different from what what you've heard about previously. And we tried to figure out who needed millions of transactions per second out in the industry. What we found in around 2011 was the ad tech market. Ad tech is a pretty interesting industry. I've been privileged to be able to work with some of the largest companies in that area because they pioneered doing a lot of predictive analytics. All of those guys who, on a millisecond by millisecond basis, are figuring out which ad to feed to you, personalizing those ads, and basing that on petabytes of data, but in real time based on terabytes of data, and all of your most recent behavior, have all been using the kind of operational architecture that I'm going to present here. This kind of architecture is really, I think of it as an in-memory style architecture. The previous guys doing stuff like this, people at Google, were all using RAM. Google, Yahoo, DoubleClick, Brightroll. All of these were RAM-based architectures and really followed the in-memory compute pattern. But what happened was, guys I started working with in 2010, 2011, they realized that they weren't going to catch up with the Googles and the Yahoos by also running RAM and running in the same kind of environment. They needed to do something different to get an edge on the established players. So what they did instead, sorry, I don't know where there's a laser thing here, but I don't know where it is. So what they did instead was they said, OK, we're going to figure out the math we need. That's your decisioning engine there. Now, instead of tying to a particular architecture and forcing all of their programmers to reorganize, learn a new language, learn Spark, learn whatever the in-memory flavor of the day is, or force their application into a particular in-memory compute grid fabric, right? You don't have to rewrite your code. What they did was they just said, look, you're going to have your own application framework, and it's going to be in whatever language you need. Because the most important thing and the most difficult thing that happens in trying to do big data and fast big data is building a team, right? That skills shortage is really what we all keep talking about in big data. So if you got a bunch of Spark guys, use Spark. If you got a bunch of guys who just want to use Java and want to have, say, a Kafka queue in between them, great, they can write raw Java. Maybe you've got a bunch of Python guys. Maybe you've got a bunch of Scala guys. Even more importantly, maybe you have different applications that need to run against the same data. This is another point where having a network hop between that application server and your core data store really makes a difference. So this is the pattern that they used. The other key element to this pattern is having flexibility to choose the balance between the amount of data and the amount of compute is absolutely critical. A lot of in-memory compute systems that you see are ones where compute and data co-reside, and it's very hard to change the balance of the amount of data and the amount of compute, right? So if you make the requirement that all nodes have to have all of the data, you've limited yourself radically to the amount of data you have. You can only have, even, let's say we could talk about the big systems, today's bigger systems, where you have a terabyte or 2 terabytes of RAM. That's still a fairly small amount of data according to a system that's trying to predictively analyze every piece of behavior and every single user on the internet in real time. Those systems are usually 20 to 30 terabytes. It would be pretty sophisticated to try to pull together a 20 to 30 terabyte RAM machine even today, let alone in 2010, 2011. They all had to use cluster compute, et cetera. Now, my database does happen to support pushing compute to the data. We actually have a system where we have an aggregation framework and a pipeline, and you can break a compute up into fragment parts and actually execute them in parallel and combine the result. Classic in-memory compute patterns. But what I have found after building that feature is very few people use it. And the reason that they use it is that this idea of having a network hop between client-server is actually a really good one. How much latency do you burn here? The amount of latency you get in a well-functioning modern network is about 100 microseconds. 100 microseconds. Which means if you can figure out the amount of data you need, spend one network round trip, you're adding about 100 microseconds to that one compute cycle. And that's 100 microseconds, don't get me wrong. I mean, compared to the, say, 10 nanos that you might be spending on RAM, that's a big, big, big difference. But the power you get of separating your data size from your compute is a massive differentiator, right? Being able to choose the amount of data later and to be able to expand the amount of data or change up your algorithms. Suddenly you need twice as much compute. Great. Those decision engines are stateless servers in either a cloud or a private cloud style environment. Go bring up some new Chef server. Tell Chef to go allocate some more servers, and you'll double the amount of compute, and everything will be great. You can even do that in semi-real time. So with this kind of pattern, with the network hop between the two, I submit to you that you can still get a lot of the power that we think of in-memory systems. And as an example, we're working with one of the West Coast payment processors, and that's one of their examples. So people sometimes ask me, why do I need 1 million transactions per second? Their answer was, they only have about 500 to 1,000 business transactions. In the case of a payment processor, that's credit card swipes. You get about 500 to 1,000 per second. Why do you need 1 million transactions per second? Because of that second component. 5,000 individual pieces of data need to be understood and folded into a particular fraud calculation in order to, according to their math, create an effective computation. Now, that business relationship there, in the case of a credit card swipe, their SLA limit is about 750 milliseconds. So they have a fair amount of time to actually get all of this done. In the case of my ad tech guys, they've got about 5 milliseconds to get their work done. They only want to do one calculation, one of those network round trips, but they have about 5 million of these happening per second. These are the ads actually flowing through real-time bidding and auctioning systems. So you can see how being able to then fit the amount of data you're doing, the amount of transactions you're doing, and really adding only about 100 microseconds, because you're not going to go and get each one separately, right? It's all basically a form of batch read in order to get all of that stuff coming in at the same time. Now, clearly, you can't get 1 million transactions per second out of a rotational disk system. This is still in memory in the sense that we're talking about chips here. But the one thing I would, if you take one thing from my talk today, I postulate to you that having a network hop sometimes between your compute and your data can be a really good thing, even for an in-memory system. And like I said, my database even supports pushing the compute into the database. It's just, which is the classic in-memory pattern. We just haven't found it to be quite as interesting as this other pattern. So what are some of the cases for this kind of in-memory compute? So the payment processing problem is fraud. What I love about fraud as a business problem is where there's money, there's fraud. So if it's advertising, oh yeah, those guys got fraud. If it's payment processing, those guys got fraud. Anything with money has fraud. Stock trading, fraud. So in the case of payment swipes, it's about 750 milliseconds. And those of you who aren't involved in that business, it's actually about accuracy. So you've got this 750 milliseconds. You want to stop the fraud, but you don't want to stop the good transactions. Because if someone says, oh, this card isn't working, they switch to another card. It flows over a different network, goes to a different bank. Your banks get upset at you if you're the payment processor, and you're blocking their money. So they really don't like that. So you have to be as accurate as possible And you're even willing to have some fraud happen in order to make sure you're not blocking too much. So their goal was to really bring to bear a variety of new algorithms. Now, they don't tell me all of the algorithms that you're doing, but let's go back to this picture here. So you've heard a lot about Spark. Just about every presentation that I've seen in the last 2 days involves Spark at some point and has involved things like machine learning algorithms. These guys, particular guys, have a set of algorithms that they believe is effective. Some of them are old fraud algorithms, what I call old, things like if you try to clear 2 transactions more than 100 miles apart in less than 5 minutes, you couldn't have gotten there, so it's likely to be fraud, right? So those are some of the easy ones that even the fraud processing engines, legacy ones, support. But the new ones tend to be a little more machine learning-ish, and they tend to involve a lot of extra new data sources. Now, of course, there's legality involved. You can't use all kinds of data and all kinds of algorithms, especially for things like payment processing, but you can in different cases. So what they want to do is build a new architecture where they can bring online entire new frameworks. They don't know. Machine learning is the flavor of the month. Is deep learning going to be in a TensorFlow system? Well, you don't want to bet on Spark if you think TensorFlow is part of your arsenal in the future, right? So it's great to have a system like this with a lot of linguistic and algorithmic flexibility. So in this case, it is a pretty simple system. And I did have the case of explaining to these guys or working with them as they transitioned from SQL to NoSQL, a large enterprise. Let me mention that for a minute. As an enterprise company, we typically do a lot of training, and there was always a fair amount of modeling work to be had here. And it turns out that a lot of the data models are exact match. Essentially, they're primary key access. You don't get these kinds of speeds by doing large-scale queries. You do them, a primary key query is the right way to do it. So often there'd be this discussion like, well, I want to have all of my behavior and have each behavioral point be a row in a database, and then I want to query on it. It's like, well, at these kind of speeds, maybe you should think of a new pattern, a NoSQL pattern, a more object-oriented pattern, where you got an IP address, just go and get that piece of data. You want to write to it, you want to update it, you want to add a little behavior. Think of your primary key and make sure that your problem is embarrassingly parallel and you have primary key access. And that gets you to these kinds of results. So in this particular case, for example, let's say you wanted to track for every IP address on the internet, every recent packet, and fold that into your fraud algorithms. So suddenly you have a 2 billion object database, plus or minus. You know, you can't cover all of China. You probably don't have all the information from there. But you certainly have billions of objects. And depending on what your data source is, you may well have hundreds of thousands of writes per second updating information from every single IP address. This is the kind of pattern that will actually allow you to have that kind of data source. That kind of data source, then you can hook up to Spark or whatever linguistically you want. Now, a second pattern that we found recently was what I call the intra-day position of record. In this case, it's all about digital transformation, and it's about a brokerage house, a well-known large brokerage house that was using a relational database to store, because it's people's money, right? It's your positions, your account status, and what you have and the amount of money in your account. They needed to still keep their DB2 system for reconciliation and reporting. That can't go away. There are too many legal constraints on the relational system and too much validation that has occurred in those kinds of systems. Any of you who have done payment processing, you know banks don't really even use SQL or rely on it. It's things like XA transactions that have a large amount of validation and a transactional workflow, not simply a database problem, but a process problem, right? So with all of that back there, how do you try to scale out your business? And being able to have a NoSQL system in front that is accurate ends up being what unlocks digital transformation use cases. So again, I believe that this is an in-memory compute problem, because what these guys want to do, again, is millions of transactions per second. In this particular case, it was mostly risk calculations. Risk calculations you can think of as primarily a in-memory compute problem. You've got a lot of things that change. You have a new piece of data. You need a calculation that needs to be redone. except these guys did it with, again, that network hop between the application and their data, and still were able to do full systemic risk calculations in under 7 minutes, bringing them down from, say, 12 hours previously. Sorry. So what are some of the other cases that are amenable to this in-memory compute with a network hop strategy? So caches are kind of like that. You can think of that as a similar problem. Retail predictive analytics should be clear from the examples in advertising. Telecom, we've seen some very interesting cases as well. These guys need to do routing decisions based on your account status. So if you have set, for example, that you want streaming to be free and throttled versus your data plan, then every single packet has to check. And if you're going to throttle, you need to know the most recent packets. So those of you who are with a networking background, imagine core routers on the internet doing a database lookup on every single packet. That's crazy, right? And yet, if you can do millions of packets per second, maybe this is starting to be reasonable. Well, mobile guys need it, so you have to go build it. So I'm going to talk to you for a second about the Aerospike architecture, and then go back to talking a bit about some of the in-memory systems. And I believe NAND, I think, has been a little underrepresented at this conference. It's really been mostly about RAM, but I think there are some trends in DRAM as well as Xpoint that you should be aware of. So in our architecture, again, we have a network hop between the client and the server. The server is a fairly classic distributed clustered system. It supports HA. And then there can be replication to remote data sources. So the system does support in-memory compute, as I mentioned, actually driving your functions into the cluster and doing partial computes, returning them and aggregating them in a client. But often it's really used in more of a key value and NoSQL style system. The system has been up and running in some customers for about 5 years. We don't have scheduled downtime. Operational systems like being able to roll a cluster node, roll in new releases, node by node without operational downtime, as well as do things like forklift upgrades. I find most of my large growing customers are doubling or changing out their entire cluster hardware every few years. Certainly if you're involved in flash and involved in NAND, that technology moved so fast over the last 6 years that after 3 years you were running on stuff that was just unreasonable. So being able to do forklift upgrades in process operationally is always a great thing to have. So one thing that we learned about NAND is that there's a lot of variation between devices. And I'll go through a little bit of some of the history of that in a minute. But what we really found was some of the keys to operational database success with NAND was the fact that NAND isn't like RAM and has thus a lot of complications. And yet it is also dramatically unlike a rotational disk. So the keys are the fact that you need to be able to read randomly very fast, and those are usually small reads. And that's the benefit, right? So if you were thinking about in-memory compute as having byte-addressable small storage, NAND can do all of that stuff. What NAND can't do is write in small local areas, unlike RAM and unlike storage class memory. So there's particular database techniques you have to use to fix that, to basically write in larger groups, and essentially we use a copy on write and block write strategy for all of that stuff direct to the device, because you can't really count on a file system to apply the kind of patterns you need. But what we found especially was we needed to figure out which devices throughout the history of NAND were great devices and which were also RANs, and which ones fell over after 12 hours and which ones were doing the number of drive writes per day that they said they were. So the key here is that most benchmarks of NAND devices in particular are all reads or they're all writes. And if you start getting involved in NAND for this kind of work, I strongly recommend you think about the impact that writes have on read performance, not just at a given moment, but when essentially defragmentation on the device kicks in. Because every device internally has defragmentation, let alone up at, say, the file system level. So where are we with NAND? And what can you do with it? in terms of in-memory compute. So where we were in 2008, 2009, 2010 was we had the first widespread commercially available NAND devices. There were other devices before that, but I really take 2009, 2010 as the beginning of the modern history of NAND. In those years, we came first with the Samsung and the Intel device really coming out with strong offerings that were fairly well tested. And I say fairly well because the Intel was in fact well known. If you wrote to it too much, it had a tendency to sort of lose all of its data and lose its mind. These were pretty early days. Things were kind of ugly out there. And Fusion IO was out there also with their first offerings, right? They were offering a much higher price point and PCIe as opposed to a SATA attach. During the years of 2013, 2014, you could put together some really amazingly fast servers that were NAND-based because you could put together SATA devices that were, say, 20, 24 devices long in a fairly commodity and cheap, widely available 2U chassis. So if you were willing to do the homework, figure out which devices were fast, figure out what your controllers were, and write some really good code, this wide SATA use case could get you some pretty amazing performance. We easily had, I put 1,500 on this slide, but I think I did actually have customers that were running closer to 250K TPS on a single 2U chassis. Again, it's clustered, so you can do a lot of other work with that and add more to it. Those were the days. In those days, we were transitioning from Intel had a very good device, the Intel 320, one of their consumer drives. They learned the lesson of having a really good consumer drive, and they stopped doing that, and they moved over to data center class devices. The other thing that happened, according to that, in that year was there's this one device that's a PCIe device, this Micron device, that broke all of our performance records since the beginning of all of our measurements. And that proved a couple of things to me. It proved how different life was going to be when we got out of this morass of SATA and into NVMe. NVMe is a PCIe style technology, but in the Fusion IO days, we had a bunch of problems. And I like Fusion IO. I know the founder. I saw him last week, and they're great guys. But they had the problem of trying to write some very sophisticated drivers. They had a very complex memory model, even within the machine, because the main CPU was doing a lot of processing, as well as the card itself. So they had to do a lot of PCIe round trips in order to get things right, and this sophisticated problem of dealing with the CPU, which meant their drivers had to be really, really, really good. They were pretty good. But one of the benefits of NVMe, and that's the world that we're in right now, is like SATA, there is this firewall, there's this protocol, transport protocol, which means the OS guys can write a really good driver. And I've seen Intel's presentation. I don't know if anyone from Intel is here. I consider them good friends and coworkers, but I think that the NVMe driver in Linux only really came of age in early 2015. It was out there, and Intel was supporting a lot of work in it, as were some other people, but it wasn't really, really good. And sometime in mid-2015, some of the core maintainers of Linux got involved and really cleaned up that driver and made it world-class. So similar to this one device, this Micron P320, which had somehow an extraordinarily high-quality driver, we're now in the world with NVMe, where we have a transport PCIe that's really fast. We have a defined protocol so that these devices stay off of the memory bus. Other than just their transfer, they don't reach back to the CPU, and there's not a lot of driver chatter going on. So really, we've gone from the sod busting days to the days when you could go fast, but it required putting a bus engine and turbocharging it in your car or something, to really a Tesla-style experience where you can get a bunch of drives, you can put them in a chassis, and they're going to go screaming fast. There's a few other things that happened along the way to NVMe, which is the NVMe controllers had to get faster because the protocol was faster. Right? If the protocol is faster, people start testing for higher speeds, and then you've got, because that was always one of the problems, was the device controllers had bottlenecks as well. So we had a fairly complex chain of technology and data movement, as well as problems in the controllers that's actually the SATA controller. NVMe, so much simpler. So these things actually go really fast. My customers love these things. They say they rack them up, they set them down, and they just work. Now, the good and bad news is these devices are still running about the same price as those NAND devices back in even 2009, 2010. They're running about $2 a gig, plus or minus. Now, prices are dropping in NAND, but they're dropping for, they're dropping for a different class of device. So as good as NVMe is, and the fact that you can actually do 1 million I/O accesses per second, 1 million per second. So those of you who saw Andy's talk earlier today, wonderful guy, interesting stuff. But I think that there's a missing point, which is if your database is only going to be doing 1 million IOPS per second, why do you need storage class memory? Storage class memory is capable of 100 times that in its raw form on the memory bus, right? If it's actually in a DIMM format. If you can do that today with NAND. Now you're going to pay 70 mics, like I said, because that is the raw lithography access time. But if you can build software that can deal with that one read being the extra 70 mics, if your compute is like that, and if you can sort of do these kind of batch operations, then you might as well use a device that is easily twice the half the cost, 4x less cost, and much, much higher density. We're commonly deploying systems, NVMe systems, where it's 10 to 20 T per small chassis, even a 1U chassis these days. One company that I'm dealing with, a company called Aperion, they're starting to ship 3U chassis with 150 T of flash that's capable of tens of millions of transactions per second. This is what NAND can do for you, and I think it is underappreciated within the in-memory compute world. Now, I just said a lot about chassis. I talked a lot about devices. But let's face it. I mean, nobody really programs on bare metal anymore unless they're kind of crazy or have a lot of money or trying to do something exciting. Everything actually happens in the public cloud. And so the good news here is that most of the public cloud providers, even though they might be about a year out of date, they do in fact have more and more sophisticated and better flash offerings. All of the major players have flash offerings, and some of them are quite good. In particular, I like what Google Compute has done recently. They're partners of ours. We've been working with them for quite a while. They have really nice abilities to mix and match the number of devices with individual instances. Also, containerization helps because containers can go out and reach out and deal with individual devices. So let's talk about what's really happening in terms of the trends of NAND. One of the things I get to do as the Aerospike CTO is we work very closely with all the flash providers. Flash providers love us because they usually run a database and there's another bottleneck. There's a lock somewhere, there's a network bottleneck, all of that stuff. Whereas we can actually show these flash devices doing high IOP rates at the speed of the device. So we get to talk with them a lot. Now, what's happening in NAND is needing to satisfy two masters right now. One of those is the master of essentially Hadoop processing and different kinds of in-memory compute that do not involve a lot of writes. So those of you who saw the paper by, I think it was Google, maybe 3 or 4 months ago, where they said most flash is only written to 10 times in its lifetime in data center environments, right? 10 times in its lifetime. Where should not be is not a common problem when you are doing very, very large compute, right? If you have a Hadoop system, if you have a data lake, enterprise data lake, you're trying to capture all of your data and leave it there. You're not transforming it, you're not rewriting it, you're leaving there. It's the lake. Everything pours into the lake. So you don't need devices that are capable of high writes. Well, that's great. You go tell the chip guys that. I speak at one of the chip conferences in Santa Clara. The chip guys have now figured that out, and they go, OK, guys, I know how to do a lithography for that. I know how to build a stack. I know how to shrink resistor sizes. And I can get you density that is amazingly good. I can drop your power levels, and I can drop your cost because I'm increasing density per chip as well. I can do all of that, but good luck writing to it more than a few times. So what you're seeing now, and be careful when you start looking at NAND because there's this growing divergence in devices. There are now devices, I put DWPD, I probably should have explained that, drive writes per day. So that is the number of times you can rip through and change every byte in the device once a day with a 5-year lifespan. So there's these devices coming out that are 1 to 2 drive writes per day. SanDisk InfiniFlash, great product. Micron has put a lot of energy into this particular market category, and they're built for big Hadoop. And you can buy things like this InfiniFlash device is, I think it's half a tera in about 3U. It's a wonderful device, but good luck writing to it. It is built for Hadoop. And it is a great device for that. So that's one area that NAND is going to. And also Hadoop, and a lot of that technology is built for rotational drives anyway. So the kind of block access that is required in Flash works just fine. And a lot of them use Ceph as their core file system for that kind of use case as well as HDFS. Now, the other half of the fence, the other master in this equation, is the kind of workload that an operational database has, not a data lake. In an operational database, you need to keep writing and writing and writing, right? You're taking in new behavior, you're kicking out old behavior, you're figuring out what's important. Those devices are sticking at around the 10 to 15 drive writes per day. And these are the devices that I believe we will still see in the $1 to $2 per gig basis. I think we've already reached really the plateau of that technology. I mean, NVMe was a big hit going forward, but I haven't seen anything on the lithography or flash roadmaps of these vendors that leads me to believe we're going to have anything radically different than this core technology that we've seen. So NVMe, 10 to 15 drive writes per day, and that's kind of it, where we've reached that point in the last 6 months, and for that class, there's nothing changing, except for storage class memory. Storage class memory is changing that entire world. Now, in my opinion, what's going to happen is those devices will be deeply challenged by storage class memory. Right now, they have a massive benefit in terms of density and in price, although we don't know the price of storage class memory, and we won't probably for what, another, at least by the end of the year, right? But storage class memory really does change the game here. Now, the way I think about it is the first essence of storage class memory, what we're going to see this year, according to Intel's public statements, is we're going to see this Xpoint stuff in the NVMe package. So it's going to look like a fast drive. Now, you know my predilection. I believe that you can use things like NAND that are in a device package over NVMe as memory. Now, I don't mean that from a technical perspective. You don't call them memmap, you don't map them. But you can use them because it's only 70 microseconds, and if you can organize your calculations correctly, then you can, in fact, make use of these, the cheapness of this kind of memory. But this is going to fix the problem that we don't have much in the way of exciting roadmap for these high-write devices. Our exciting roadmap in high-write devices is going to be this. Because you can write like crazy to this thing. It has really no limit in terms of wear. It's easily, according to what Intel says, I think about 1,000 times better in terms of wear than anything else. Now, I'm not convinced that's necessary because these 10 to 15 DWPD numbers, I rarely see cases where anyone pushes that. If you think about the amount of density and the amount the data changes, even if you're taking as a flow all of the behavior on the entire internet, 10 to 15 works, and most people don't have cases that are much more than that. But this stuff is faster. What Intel is saying for their NVMe devices is it will be about 7x faster than using even the fastest NVMe. Now, as lithography, we know it is about 2 orders of magnitude, at least 100x faster in latency and throughput. But they have to go through the NVMe package. So they have to take the transport and get everything over the transport and have a controller and all that jazz. And all of that basically sucks latency. So what's happened is the world has shifted. It used to be the bottleneck was firmly on the device, on the lithography side in terms of getting in and out of chip. And the controllers, they could be not that high powered, and the transport, it's really, once we got to NVMe and PCIe, wasn't really the bottleneck. And Xpoint flips it all back over and says, transport guys, you need to find a new trick. Well, and that new trick is obviously NVDIMM. So once you put this device in an NVDIMM package, and Intel has to basically rev the DIMM specs in terms of supporting persistence, not the physical packaging as far as they've explained, but you certainly do need all of the back and forth about what persists and what doesn't, and you heard Andy talk about pcommit, et cetera. So, but the thing is, we don't really know when this is going to happen exactly. But my point is that I believe that that packaging competes with RAM more than it competes with storage. It's not really storage. It's closer to RAM. Now, architectures that think of storage or think of devices as just, oh, it's just a bunch of tiers, and you have the hot stuff, and you sort of flip everything out and age it out. That's not the style that I tend to approach when I look at these problems. When I think about trying to build high-performance software, I think, first of all, about the fastest storage. The fastest storage is not RAM. The fastest storage is what's in your L1 and L2 caches. That stuff is now 100 times to 1,000 times faster than RAM. We work really hard at Aerospike, and some of the companies I've invested in really managing that cache. We're trying to call that on-silicon computing, because it's a little tighter and a heck of a lot faster than having to flip all the way out to RAM. Your second storage tier, so that's my first storage tier. Well, memory tier is what's in, and you have to manage it. You can't just, even though Intel does a great job in their cache controllers and cache algorithms, I can't count that that algorithm is going to work for the compute pattern that I'm using. So then you think about a RAM, which is 100x slower, and across that what starts to look like a slow memory bus. With the advent of Xpoint, we're going to see a new class of devices, which is 100x slower, roughly, according to their published numbers, than what's on RAM. But on the other hand, at much higher densities and at much, much, much lower power draws. Right? The whole game has changed. And there's some slight differences in what the granularity of reads and writes are, but we all think that those aren't that big a deal. And then you've got NAND flash way out, now seeming to be way out on the slow end. First of all, it's across a much slower bus. It's across PCIe, and it's got this 70 microsecond delay on every read. So let me leave you with a few of the ideas about how we're starting to think about these architectures. So I think that the fact that Xpoint is persistent is underappreciated in software, deeply underappreciated. With RAM, if you make a mistake, you restart your computer. For many, many decades, we've been thinking, oh, if you're right in the middle of one of these commit cycles and things kind of go wrong and I have a certain kind of power glitch, I'm going to reboot my system. That's not going to work in these cases. And Intel's put a lot of energy and research into how to build data structures for it. They have some really groovy libraries that they're publishing. But I think we're all going to have to start thinking really differently. And this is one of those turning points, again, Andy's wonderful talk earlier, where you go, oh my God, the world is going to change. We're going to have a RAM-like substance where we can't just reboot the computer. We're going to have to think about storage in a very different way. And I probably can't say anything too much more than that. In most cases, I think the interesting case is really to think of it a lot more like RAM than to think about it like storage. In particular, in the Aerospike architecture that we're starting to work on with Intel and the simulators, I'm thinking about it more like an index. Having a hybrid system that uses NAND as your bulk store, but uses the fast update speed of a system and parallelism and low latency, right? The fact that Intel can show queue depth speeds of 1 and still hundreds of thousands of transactions per second, that's how they say it in storage land. In in-memory compute, you think about it differently. But essentially, this is a device that will be uniquely suited to storage, but I think that, uniquely used for indexes. and really good at a variety of different kind of multidimensional and fat indexes. But to me, there's still a place for using NAND, because having a larger bulk store that is 2 orders of magnitude further down the road, now I've only got 4 tiers to deal with, and so life gets a little more interesting. I've got on-chip, I've got RAM, I've got Xpoint, and then I'm going to have NAND, and all of them are rather pleasantly about 2 orders of magnitude in speed and latency away from each other. So that's how we've started thinking about this problem at Aerospike. So I think we have about 5 minutes left. Any questions? No icebreaker questions? No nervy people? OK, well, hopefully that was an interesting introduction, and hopefully you've thought a little differently about storage in-memory compute and how you might be able to either use NAND or networks in some of your compute. So thanks very much.